Robots are starting to move past reactive control and into a new regime where memory, planning, and imagination are all being fused into the policy itself. That matters because the bottleneck is no longer just whether a robot can see the world, it's whether it can preserve depth. Remember what happened 5 steps ago, and imagine futures that actually line up with the task. This week's results point to the same trend from 3 angles: richer 3D guidance, latent native memory, and video-based reasoning that trains the policy. Keep watching, the details explain why these systems are suddenly getting much more reliable. Let's explore the first paper, 3D hamster bridging planning and control in hierarchical vision language action models through 3D trajectory guidance. 3D hamster, from the KAIST and Crafton AI collaboration, addresses a core failure mode in hierarchical vision language action systems. Planners output 2D waypoints that low-level 3D policies must unproject, creating depth ambiguity and the graffiti effect on point clouds. The method upgrades a pre-trained Quen 3 VL8B instruct planner with a dedicated depth encoder and a dense depth reconstruction objective, so it predicts metrically reliable U-V-D trajectories that are directly consumable by a point cloud-based 3D policy, specifically 3D flow match actor. On Droid Spatial Bench, built from 148 held-out Droid pick-and-place episodes, the full model reaches 65.5% on the strict 10 centimeters, both metric versus 60.1% for RoboBrain 2, 58B, and 29.7% for Gemini 3, 0 Pro at 5 centimeters. In Coliseum simulation, 3D guidance raises average success to 44.8%, outperforming 2D hamster at 38.8% and the unguided baseline at 36.6%, with especially strong gains under lighting, object, and texture perturbations. On a Franca Panda robot, the 3D planner achieves 80% on button pressing, 68% on pouring, and 62% on pick and place, beating both hamster and the monolithic Pi 05 model on average, and showing the largest advantage on pouring, where precise depth control matters most. Let's explore the second paper, Dual Latent Memory in Vision Language Action Models for Robotic Manipulation. LaMEM VLA introduces a dual latent memory architecture for robotic manipulation that moves historical experience into the native embedding space of vision language action models instead of treating memory as external. Policy-side context. Built on a 7B parameter prismatic VLM backbone and a diffusion action expert with approximately 300 M parameters, it splits history into a short-term visual vault and a long-term semantic action continuity vault, retrieves task-relevant evidence with a context-aware query, compresses it into fixed-length latent tokens, and weaves those tokens directly into the reasoning sequence before action decoding. This design targets the Markovian short horizon bias that limits long horizon manipulation. On Simpler and Bridge, LaMEM VLA reaches 73.9% average success, outperforming CogAct by 16.6 points and Pi 0 by 4.7 points. On Libero, it achieves 97.6% average success across 5 suites, beating Memory VLA by 1.1 points and CogAct by 4.4 points, while reaching 97% on Libero, 9-0. Ablations show that removing both memory streams drops performance to 57.3% on SimplerEnv and 92.1% on Libero, 9-0, confirming that latent native integration, not just retrieval, is the key gain. Let's explore the third paper, RoboTails Learning Reasoning Guided Robot Policies via Task-Aligned Simulated Futures. RoboTails, from the University of California, San Diego, reframes robot control as task-aligned imagination by coupling a pre-trained stable video diffusion backbone with hierarchical reasoning and policy learning. A Gemini 2.5 Pro LLM planner decomposes each instruction into 2 to 5 ordered subgoals. The resulting plan conditions the video generator, and a frozen VLM critic provides DDPO-style reward feedback that steers the denoising dynamics towards semantically faithful futures rather than merely realistic ones. Those learned decoder features then condition a 1D action diffusion UNet, with action gradients flowing back into the video generator in a single-stage joint objective. On RoboCasa, the method reaches 64% average success across 24 manipulation tasks, improving over video policy and the strongest prior baseline, and on Libero 1.0, it achieves 97% average success across 10 tasks, versus 94% for video policy. The paper reports especially strong gains on structured long horizon behaviors such as turning, pressing, and pick and place, while ablations show that planar injection alone is insufficient without joint training and critic feedback. Additional analysis finds the critic reward is calibrated to success with AUROC 0.72, and joint training also improves general video generation fidelity on UCF 101, reducing fraîcheur distance from 660 et 15 to 240, true set, and MMD RBF from 240 et 9 to 60, true 1. That's a wrap on today's AI paper highlights. Thanks for watching.